Friends, hydrogen warns you. Methane guides you. But ethane tells you one critical truth. The fault is no longer just starting. It is evolving. Ethane is called the transition gas because it sits exactly between low temperature stress and developing overheating. Most engineers either confuse ethane with methane or wait until ethylene appears. And that delay is where insulation life is lost. In today's Electroverse episode, we will decode ethane, C₂H₆, in transformer DGA. Why ethane is formed inside oil. What temperature range it represents. Difference between methane versus ethane behavior. Why ethane is a warning before ethylene. How ethane trends predict future overheating. And how senior engineers use ethane to act early. Stay till the end, because ethane is the gas that tells you still have time, but not much.
Welcome back to Electroverse, where transformer gases tell a story and engineers learn how to read it correctly. Today we move further along the thermal path. We are talking about ethane, the gas that tells you heating is real and it is increasing. If you've been following our DGA series, you know we started with hydrogen, the universal indicator of electrical stress. Then we covered methane, the gas that signals heat has started. Now we reach ethane, written as C₂H₆, the bridge gas between early heating and serious overheating. Think of ethane as the transformer's way of saying, this is no longer just starting. This is confirmed thermal stress. When you see ethane rising in your DGA depots, the heating inside your transformer has moved beyond the initial stages. It has become sustained and, more importantly, it is increasing. According to IEC 6599, ethane is generated when transformer oil is exposed to moderate thermal stress. The temperature range we are talking about here is typically between 150 degrees Celsius and 300 degrees Celsius. This is where things get serious for your transformer's health. Let me break down the standard limits for you. Based on IEC 6599 and IEEE C57.104, normal condition means ethane below 20 parts per million. When you see readings between 20 and 90 parts per million, you are in the caution zone. Anything above 90 parts per million puts you in abnormal territory, and that demands immediate attention. But here's what makes ethane particularly important in DGA interpretation. It does not just tell you about current conditions, it tells you about the progression of thermal stress. When you see ethane present with methane, but low ethylene and zero acetylene, you are looking at moderate oil heating. This could be from long-duration overloads or cooling system limitations. The good news? This is still a correctable condition. However, when ethane starts increasing together with ethylene, that's your signal that temperatures are crossing safe limits. You are now dealing with severe hotspots and accelerated insulation aging. The heat that started as a manageable issue is now becoming dangerous. Rising ethane means heat is sustained. Unlike the early warning signals from hydrogen or the initial thermal indicators from methane, ethane tells you that heating has become established in your transformer. This is where the engineering decision-making becomes critical. Ethane is what we call a decision gas. Ignore it and problems escalate. When your DGA results show rising ethane levels, you need immediate load assessment. Check your cooling system performance, conduct thermal inspections, implement trend-based DGA monitoring. These are not suggestions, these are engineering imperatives. The beauty of understanding ethane in the context of DGA progression is that it gives you a clear roadmap. The thermal fault progression typically follows this pattern. Hydrogen indicates electrical stress, methane shows heat has started, ethane confirms heat is sustained, and ethylene warns you that hotspot conditions are developing. Ethane tells you heating is established, ethylene tells you heating is dangerous. That distinction is crucial for your maintenance strategy and operational decisions. What makes ethane particularly valuable as a diagnostic tool is its position in this thermal progression. It's not an early warning like hydrogen, and it's not a critical alarm like high ethylene or acetylene. Ethane is your strong corrective signal. It's telling you that you still have time to act, but that time is limited.
When you see ethane levels rising, you are looking at a transformer that is experiencing sustained thermal stress. The oil temperature has reached levels where molecular breakdown is occurring consistently. This is not a failure alarm. It is a strong corrective signal that demands engineering action. The corrective actions for high ethane are straightforward but critical. First, Assess your load conditions immediately. Are you running the transformer beyond its thermal capacity? Second, evaluate your cooling system performance. Is the cooling adequate for current operating conditions? Third, conduct thermal inspections to identify hotspots. Fourth, implement more frequent DGA monitoring to track the progression. Remember, ethane formation typically occurs when oil temperatures are between 150 and 300 degrees Celsius. At these temperatures, the oil is breaking down at a molecular level, creating this specific hydrocarbon signature. The presence of ethane confirms that your transformer is operating under thermal stress that goes beyond normal operating conditions. In practical terms, when you see ethane in your DGA results, you are looking at a transformer that needs attention. The heating is real, it is sustained, and without corrective action, it will progress to more severe conditions. This is where proactive maintenance makes the difference between a long-lived transformer and an expensive failure. The engineering interpretation of ethane in DGA is clear. Sustained thermal stress requires sustained corrective action. You cannot ignore rising ethane levels and hope the problem resolves itself. The physics of thermal decomposition does not work that way. Ethane is a bridge gas between early heating and serious overheating. When you understand its position in the thermal progression, you can make informed decisions about transformer operation and maintenance. You can take corrective action before the situation escalates to dangerous hotspot conditions. Control heat early, and transformers live longer. That is the fundamental principle behind effective DGA interpretation and transformer maintenance. Ethane gives you the information you need to control heat before it becomes uncontrollable. In our next session, we will explore ethylene, the hotspot gas that signals dangerous thermal conditions. Until then, remember that ethane is your decision gas. When you see it rising, make the decision to act. Your transformer's longevity depends on it.
So friends, this is the real meaning of ethane, C₂H₆ in DGA. Ethane does not indicate an instant failure. Ethane indicates fault progression. It tells you oil stress is increasing, thermal energy is building up, and insulation is slowly losing margin. Remember this simple ladder. Methane means the fault has begun. Ethane means the fault is evolving. Ethylene means overheating is accelerating. If this explanation added clarity to how you read DGA reports, then please support Electroverse. Like this video, it helps this technical knowledge reach more engineers. Comment below, have you seen ethane rise before ethylene in your transformers? Subscribe, because this channel builds DGA knowledge step by step, gas by gas. Your engagement helps this content stay free, technical, and honest. In the next episode, we decode ethylene, C₂H₆, the gas that confirms active overheating and demands action. You've been watching Electroverse, where every spark tells a story. Stay charged, stay safe, and happy.